is the fourth lecture of this course on moduli and stacks. And yeah, and today we're going to it's an important lecture. Monday's lecture, we covered groupoids and pre-stacks, which I'll quickly review. But then today we're going to introduce probably the most important notion of the class of pre-stacks. But let's first give a quick recap of what we did last time. So we introduced the notion of a pre-stack, and I'll walk you through this definition again. So we first fixed, right now we're just fixing an arbitrary category, S. And then we say a pre-stack over S is a category X together with a functor to the category S. And so you think of this category X as having objects like maybe A and B, and these objects A might live, they project under this functor P to a scheme S. And then we say that this morphism alpha from A to B is over the projection morphism of schemes S to T. And then there's two important axioms for it to be a pre-stack. The first is that, for all diagrams, whenever you have a morphism of schemes S to T and an object B over T, then there exists an object A together with a morphism over S to T. And the second property is that this pullback satisfies a universal property. So this is the pullback. And moreover, that any map satisfies this universal property, which is that if you have, so any map A to B satisfies this property. If you take a third object, A prime, and you sort of view it, suppose that A prime maps to B, and the only way to formulate really that A prime maps to S is to say that it lives over a scheme S prime, and that maps to S. And so given such data, the condition is then that there exists a unique arrow completing this diagram.
So one thing that when in that condition right there, that map from A prime to B, are we assuming that that's like sitting over the map, the composition of S prime to S to T, or is it, does it not have any connection to the bottom?
Yes, yeah, right. Yes. Like the map, right? The map from A prime to B sits over S, the composition S prime to T. Yes. Thanks.
Sorry, in the first diagram, there's that purple arrow from A to S. Is that one like filled in?
So when I write this, you mean the vertical map?
Yeah, from A to S.
So when I write this, all this is meaning is that S is the projection of A. So it's not really a map. It's just saying it lives over this map of schemes.
Thank you.
Right, so that was the fundamental definition of a pre-stack. And when you have a pre-stack, we introduced this notion of a fiber category. So X of S, and the objects are simply objects of X over S, and the morphisms are all over the identity in S. And the exercise from last time was to show that these axioms imply that this category is a groupoid, meaning all morphisms are invertible. And we had, let me just quickly recap these important examples from last time. First and foremost, schemes are examples of pre-stacks. So if X is a scheme, we can take the category actually of schemes over X. So here an object is just a map from S to X, and this lives over the category of schemes where this object projects to S. And and this is an example. This is an example of a pre-stack. And the reason these axioms hold is because morphisms to schemes compose. And I mean, the main example in this whole class is the moduli space of smooth curves, MG. And here, this is defined as the category where the objects are smooth families of curves. And an amorphism in this category is a Cartesian diagram. So maps the data of a map from C to C prime and the data of a map from S to S prime such that the induced diagram is a fiber product. And yeah, and so this is MG over the category of schemes is a pre-stack. And these axioms are satisfied just simply because we have pullbacks of schemes. And the pullbacks satisfy a universal property. And then getting to morphisms, to recap that a morphism of pre-stacks is just a functor, but we require that this diagram strictly commutes. Meaning that if you have an object of X, it's that object and its image under F live over the same object in the category S. And then because we're considering, because morphisms are functors, we also have the notion of natural transformations between functors. So we have this notion of a two-morphism. Oh, that was the eraser. A two-morphism is simply a natural transformation. And we use this sort of convenient notation of like, drawing a map with actually two lines to indicate that it's a two-morphism. And then once you introduce this notion, whenever you talk about commutativity of diagrams, if you don't, you can talk about two commutativity. So a two commutative diagram is also the data of this two isomorphism between their compositions. Right, and the last thing I'd like to summarize is that we have the two Yoneda lemma for pre-stacks, and which is this assertion I summarized here. And maybe the important consequence of this, I mean, the upshot is that a map from a scheme S, or I guess I'm just in an arbitrary category S, is the same data as an object, A in X of S. And maybe as an abusive notation, we're going to conflate the two. So we'll just, often without mentioning it, pass between a morphism from S to the pre-stack and an object over S. And the last piece of the material that we need to discuss of pre-stacks that we didn't introduce last time was fiber products. And so let me give a quick discussion of fiber products of pre-stacks. And the goal here is to, if we're in the setting where we have sort of two morphisms, F and G of pre-stacks, what we'd like is sort of another pre-stack sitting up here and maps to it, satisfying a universal property. And so first I'm going to give you a construction of this, and then I'll show what property it satisfies. So here's the construction of this fiber product. Objects are triples. And here, let's spell this out. X is an object of X, Y prime is an object of Y prime, and they're over the same scheme. Or same object, I shouldn't say scheme. The same object S. And then gamma, so I could take f of X this is then an object of y, and I could take g of y prime, and gamma then is a isomorphism between those two objects. And this is over the identity in S. And maybe before I go sort of further, what I did do last time is I discussed groupoids. I discussed fiber products of groupoids. And so maybe a consequence of this definition is that the fiber category of this fiber product.
Sorry.
Yes?
Isn't the fx exactly S and gy prime exactly S?
Wait, no, these are objects in Y.
And S also is in Y, right?
No,
no.
S is in this category,
yes.
script S.
Okay, thanks. Okay,
Yeah,
thank you.
But right, as a consequence of this definition is that the fiber category of the fiber product should be the fiber product of the fiber categories. So if you're only interested in looking at the fiber categories, you just need to consider this as a fiber product of groupoids. Right. So okay, but let me also tell you what the maps in this category are. So a map between these two triples should be the data of a map from x1 to x2. We'll call that chi, and a map from y1 prime to y2 prime. Let's call that gamma prime. And then if you compose these, so you and take the images of both chi and gamma prime into the pre-stack Y, they need to satisfy this commutativity diagram here.
Sorry, so there's no Q actually?
Maybe I missed that. What?
You're right, is a triple Q chi gamma prime.
Oh.
Is this diagram supposed to be too commutative?
Oh yeah, Q should be Q is right. Q is then if this object is over S. Sorry, if this object is over S and this is over say S1 and this is over S2, then Q is the map between them. But let me tell. Yeah. So what this gives then is a pre-stack here, and it's clear that we have these natural projections both onto X and onto Y prime. And I also claim that there's a two commutative arrow here, and maybe I'll do that at the bottom right hand side here. Alpha is this goes from P2 composed to G to F composed with P1. And so this is a two morphism. And to specify what that is, well, I need to tell you that for every object, for an object X, Y prime gamma, that this, if evaluated on this object, should be a morphism between the, I take this object here and I look at it, two images under both of these compositions. Under the composition where I go P2 to G, then it's just G of X. What, no, I think it should be F of X. And then it should go to G of Y prime. I need to specify two morphism, I need to specify a map like this for every object, and this map is precisely just gamma. So gamma gives you that two isomorphism. Yeah, it's really a mouthful here. Fiber products of pre-stacks are genuinely confusing, and it's one of the things you need some practice to get a handle on. And so this constructs a pre-stack, and so I've constructed it with these projections and with a two commutative diagram. And then in this theorem, I state the universal property, which I'll walk you through now. I guess what I've given, maybe this is, I've written alpha the other way. Maybe. Right, so here's the statement. The claim is that this fiber product satisfies the following universal property. Whenever I have another two commutative diagram, which is the following data, which is a pre-stack T, a map Q2, a map Q1, and then a two arrow tau between them, the conclusion that is that there should exist a morphism H. So there exists a morphism H together such that these two triangles should be two commutative. So there's a two arrow here beta and a two arrow here gamma. And these two arrows, tau, gamma, beta, and alpha, need to satisfy a natural compatibility condition, which is this condition here that I just write down. I mean, I can't really give an intuitive explanation of it, other than it's like the natural condition that arises when you try to compare these. Any questions on this? So I think it's, yeah, let's turn to examples. So I'm going to give two examples of fiber products of pre-stacks. And the first is sort of this interesting example where I take, I'm going to define a MG1. And here the objects are like an MG, but you also have a section. So an object is a family of smooth genus G curves together with a section. And like with MG, morphisms are Cartesian diagrams, but they have to be compatible with the section. So this defines a pre-stack. And then MG1, and then if you forget the section, you get a map to MG. So here the map takes a family with a section and just forgets the section. And now let's take an arbitrary morphism S to X. So let's fix a map. And then by the two Yoneda lemma, this corresponds to a family of curves. And the exercise is to show that, in fact, that family of curves is the fiber product. So in other words, sort of the consequence is that this is the universal family, because any family of curves is the pullback from it. And this also sort of makes sense because if you think about the data of MG1, like if you just restrict to objects over the complex numbers, the data is a curve, a complex curve together with a point. And then therefore the fiber under this map, since the additional data is a point, the fiber should be the curve. You just, And in our second example, turning to this side, this is also going to be an important example of a fiber product. So the starting point is we first take a pre-stack X, take A and B to be two objects over a scheme T, and then we define this we define this pre-sheaf called the Isomorphism Pre-Sheaf, which is a pre-sheaf on the category of schemes over T. And it's defined by sending a scheme S over T to the set of isomorphisms between the pullbacks of A and B in the fiber category of X of S. And so this defines a pre-sheaf. And then the exercise is to show that, that you have a Cartesian diagram where this is the diagonal. And then this map is induced by A comma B, and that isom sits here. And if you take a step back and just think about like, oh, what if this what happens in the case that the stack X is a scheme, then this diagonal is a monomorphism. And if you have two maps from a scheme T to a scheme X, then this fiber product is the equalizer. And since schemes, since morphisms of schemes are either equal or they're not equal, like this equalizer is sort of a sub-scheme of T. Since now we're working with pre-stacks, there's many ways how morphisms can be equivalent. So what you get is actually a sheaf over T, and this is not a monomorphism, right? The fibers parameterize the set of isomorphisms. Great. I think before turning now to stacks, I'd like to pause, and take questions if there are any.
I have a question. When I was working out like the universal property for the fiber product of groupoids, it seemed like you could describe it as saying there's a unique functor. Like if I have, a map and a natural transformation that witnesses the commutation, there's like a unique functor to the fiber product that makes it strictly commute. Or it seemed like you could say there is a functor to the fiber product that makes it commute, and maybe you could say it's like unique up to unique natural isomorphism. I'm not exactly sure I don't know. It seemed like here you were saying you can describe these natural transformations to witness the commutation.
Mm-hmm.
And I'm wondering if that's like advantageous over just saying there is a functor that makes it strictly commute, or is that meant to be avoided here?
So let me turn down. So to say that,
like the uniqueness of H seems
right. So here I didn't say anything. Well, okay, I guess. Right, I didn't say what the uniqueness properties are. Yeah, the H and the two isomorphisms should be unique up to unique isomorphisms themselves. Yeah, this is very confusing. I don't think I'm going to have a good answer for you. I think you have a really good question. I'm not sure if I can address it succinctly in a way that's very helpful. But I think, yeah.
I mean, it seems to me like you could describe H so that they commute on the nose, and I'm wondering if that's to be avoided.
No. I mean, if you can get it to commute on the nose, that's better. I mean, I'd have to sit down.
At least on the level of groupoids. I mean, maybe I just confused myself. I didn't sort of try to glue it to this pre-stack definition, but at least on the level of groupoids, it seemed like you could describe it. Anyway, I believe you. Yeah, but I always get confused with these these two isomorphisms myself. So I'm gonna try to avoid saying something wrong. Okay. No worries. Thank you.
Yeah, you can ask other questions. I won't promise to answer them, but you can ask them.
Could you go forward to the slide with the isom? I'm just having a little trouble seeing how isom has the structure of a category fibered over S.
Oh, good. That's a good question. Yeah, here I'm sort of using notation. I guess here I'm working in the category of schemes. So already we're viewing a scheme T as a pre-stack via that construction, but we're also, every pre-sheaf can also be viewed as a pre-stack. So that's really how we're viewing the isom as a pre-stack. So you can think of so this viewed as a pre-stack, if you want to know what the fiber category is over a scheme S, it's just the sections over S.
But S is assumed to come equipped with a map to T?
Yeah.
In order for it to, so it seems like it's...
right, so I guess, so this is naturally... Right, so maybe now I see your question. So this is naturally a pre-sheaf over T, and therefore a pre-stack over schemes over T, but then I could just further compose and view it as a pre-stack over all schemes.
Just via the map of schemes over T mapping to all schemes.
Yeah. But yeah, these are all good questions. Right. So now I'm gonna introduce the notion of a stack.
Sorry, Jarod.
But wait, go ahead.
So I just want to make sure that I'm understanding like the moral idea here. So like when we start talking about the stack, well, the pre-stack idea, it seems, is that like you have families of curves, but then you can sort of augment them with the isomorphisms or the automorphisms of that curve. And then this pre-stack idea is morally saying like, oh, a pre-stack is something that something where we can forget that augmenting, like we can forget the isomorphisms that we've brought along with the object. Does that make sense? So like the fibers are the groupoids, which consist of all the isomorphisms from the object to itself. And we're forgetting that in some sense when we go down. Is that,
I'm not quite getting that, but yeah, I don't quite, I don't quite follow what you're trying to say here.
So it's like the problem that we talked about earlier in the course is that a family of curves comes with a bunch of automorphisms.
Mm-hmm.
And then this is what causes us to not have
representability, right?
A scheme. So now we're saying, okay, so let's augment these objects, these families, with their automorphisms, like the set of these things. And then we're saying that, oh, we can forget that set if we want, and just go back to a scheme or.
Well, in some sense, okay, yeah, okay, I think what you're saying, well, yeah, right. If you take the stack as I define it, MG, and then you just consider the functor that takes a scheme S to the isomorphism classes of objects in that groupoid, you get precisely the functor I defined earlier, which is not representable. That's right. So yeah, if you forget that data, you're back to where we were.
Okay. All right. Sorry. I could think more about.
Yeah, and then, but maybe later is that there's something related is that the coarse moduli space for MG won't represent that functor.
Okay. Thank you.
So I've cheated again and written the definition that I'll try to walk you through. So now we fix a site S, so it's topologized. So and we define a stack over a site S. It's a pre-stack first of all, and it has to satisfy some natural gluing properties with respect to coverings. So the idea is that like a stack should be to a pre-stack as a sheaf is to a pre-sheaf. And we just need to require that morphisms and objects glue. So that this first axiom is that morphisms glue. And the way to set it up is let's take two objects A and B over S, over the same object S. And then suppose we have this commutative diagram of solid arrows like this. So in other words, you have maps from the restriction of A under this cover to B, and then the claim is then that there should exist a unique way to fill it in. So I mean, this is exactly saying that morphisms glue in the topology of S. Locally, you have a covering of your object A and maps to B, and then it should glue uniquely. The second axiom is trickier because it's about objects, and morphisms, you can just say when two morphisms are equal. Objects, you have to declare an equivalence between them. And so there's this additional level of complication. And so what we start with is objects AI over SI. And then you and isomorphisms on their pullbacks, and such that they satisfy this condition. This is sort of a natural cocycle condition. And then if they satisfy that cocycle condition, then the conclusion is that there should exist, there should exist an object A together with these maps to it over, the coverings of S. Yeah, that's all it is. I mean, that's the definition. Morphisms in objects glue.
Jarod, I've got a question. I think I probably forgot something you did earlier. Did you define pre-stacks in a way that morphisms did not satisfy the identity axiom, and so you have to actually put those in too? Like two morphisms are the same if they are the same on a cover. Was that was there earlier?
I don't think I did that.
And then don't we need? I'm 90% sure I'm confused. I'm one confused.
Wait, you're asking about two morphisms?
Well, that's
I think I'm confused too now.
I mean, it's secretly about two morphisms, but let me say it in terms of morphisms. It's an isom. It's like isom is let me phrase it differently. Isom is a sheaf, which means isom satisfies a gluing axiom and identity axiom, and the identity axiom is not. Is that already implicitly, like, is there a zero?
Well, I think there's a uniqueness in this part. There's the exist and there's the uniqueness. I think this, maybe I formulated things partly.
Perfectly, perfect. You didn't separate them out. They're just together.
Yeah, right. So what Robbie's is saying is that this entire first axiom here, is axiom 1, should be equivalent to like the condition that all of these isom sheaves A, B are all the isom pre-sheaves are sheaves. Yeah, thank you. And maybe another way to think about this condition is sort of similar to the sheaf condition we have, but it's with like you can view X objects over S. These map by pullback to them objects over SI. These map to objects over Sij, and then they map to triple intersections. And then you could say that this is exact. Whoops. But whatever that means. And if you try to spell out what exact means, you'll get exactly these conditions. Right, it's sort of going from the sheaf axiom one level further to triple intersections. So if you spell out what exactness means at this step, yeah.
I guess I'm implicitly looking at your 1 and 2 and thinking it's really 0, 1, and 2, and like and just because like you have 3 things in the like single arrows, double arrows, triple arrows, that somehow there's 3, not 2, rather than.
Yeah, this will come up again later with stackification, whether it's a 2-step or 3-step process, depending on how you count. But I see what you mean.
In the second condition, could there be multiple A's in X? There's not a uniqueness.
Right. Yeah, there's no uniqueness in that, but the axiom 1 will then give you, we'll say that if you have any 2 satisfying, any 2, then they're going to be uniquely isomorphic. So let's turn to some examples of, and so the first example is going to be Sheaves R Stacks. And so here, let's take F to be a pre-sheaf. And then you can build from this a pre-stack, where the fibered category over S is just F of S. And then the statement is that F is a sheaf if and only if X of is a stack. And our next example is one of my favorites, and I think this is really how I learned intuitively what a stack is from Barbara Fenteke's notes, Stacks for Everyone. She emphasizes, sorry?
Sorry, I have a question about the sheaves or stacks. So like the definition of a sheaf, if you look at sort of the exact diagram there, is that sort of the first arrow and then the double arrow, that is exact. And then the fact that sheaves glue is that the double arrow to the triple arrow is also exact. Is that correct?
Right.
Okay.
Yeah, but specifying what this exactness means here is something maybe for higher category theorists.
Right, just, yeah, spiritually speaking.
Yeah, exactly. Right, so and so going now back to example 2 is, I want to emphasize how like the sheaves naturally form a stack, and it's kind of a nice example. And so here I'll define QCO is going to be, as a category, it has objects which are just like pairs of a scheme and a quasi-coherent sheaf. So S is a scheme and F is a quasi-coherent OS module. And then similar to how we were discussing last time, morphisms, say from S to F, from S prime to F prime, should be the data of, well, first a morphism of schemes, and then you should have a morphism, say F prime to F push forward F, a morphism of quasi-coherent sheaves, say of sheaves such that, of OX modules, say, such that the pullback is an isomorphism. Right. And so I want to say, you already know that QCO is a stack over the big Zariski site. And in fact, this just follows from like exercises in the first chapter of section 2 in Hartshorn, that sheaves glue. I mean, here I'm dealing with quasi-coherent sheaves, but it's the same story. And if you spell out, like this exercise says that there's 2 parts here, and this first one is precisely axiom 1 of being a stack. And the fact that sheaves glue, and when you, because sheaves have automorphisms, you also need to specify this co-cycle condition. And so I guess, what I'm trying to emphasize here is the gluing condition for sheaves that you're already familiar with implies that the stack of sheaves, that the pre-stack of sheaves is a stack. And then if I restrict to quasi-coherent sheaves, it's also a stack. And then a tau descent for quasi-coherent sheaves implies that this thing, as I've defined, is also a stack over the big tau topology. Right. And so I think a lot of people get kind of stuck on some of these technical notions, specifications in the definition, but but it's a condition you're already familiar with. I'll do another important example. And so I've just repeated the definition on the left-hand side so you can see it. And I'm going to define the stack of all families of schemes. So here, let's define, I'll call it FAM over schemes. And here, an object is just a morphism of schemes, arbitrary morphism of schemes, and then a morphism between 2 maps of schemes is just a Cartesian diagram. And then here, right, then like this, a family X over S gets mapped to S. And so this is like a very large stack parameterizing all families. And if you think about it, like the one example we had of MG is sort of a substack of this, right? MG was the same definition, but we restricted to maps which were smooth proper morphisms such that all the fibers were G as G curves. And so here we're parameterizing all families of schemes, no condition on the morphism whatsoever. But nevertheless, we know that this is a stack over the big Zariski site. And the reason, well, the axiom 1 is just that morphisms glue. And if maybe it's worth spelling that out. So let's suppose we have objects A and B over some scheme S. So these correspond to morphisms of schemes B. And then we have a Zariski cover. This is an open cover, and such that if you take the restriction of XA to each SI, and we have maps to XB, then the claim is that then they uniquely glue. And this is the fact that that morphisms glue in the Zariski topology. And the second axiom is that schemes glue. And here we need the cocycle condition. And the setup is maybe you have a scheme XI over SI, and then and then you have isomorphisms between the restriction over SI. And what we're trying to build is then some family of schemes X over S. And the point is that, is that you can glue schemes. And this is precisely the cocycle condition, from this exercise in Hartshorn over here. So if you translate what gluing for schemes is, it gives you this scheme X over S. So this is a stack over the big Zariski site, and maybe I should emphasize that it's not a stack over the big étale topology. And this is because we can only glue schemes in the Zariski topology. A scheme is, by definition, you're gluing affine schemes in the Zariski topology. In order to get a stack over the big étale topology, we'll need to glue schemes in the étale topology, and then we'll have to work with algebraic spaces. So if you just replace, X here with an algebraic space, then it will turn out to be a stack. But we'll see that later. And maybe for the most important example, let's now turn to MG. And I want to show that. So I'm going to use a property about families of curves here, because as we just saw, is that for arbitrary families, that they do not form a stack in the big étale topology. So we need to use something special about curves, and it's this fact. So here I've just defined or recalled precisely what we mean by family of smooth curves. And we'll use this property, which is a nice, simple consequence of cohomology and base change, which says that if you have a family of curves of genus at least 2, that the relative canonical is at least the third power of it is very ample, and the push forward is a vector bundle. And I think, we'll have similar facts later for stable curves, and maybe I'll revisit this later, but it's a nice consequence of cohomology and base change. And I think it's important to point out that, this is one of the important applications of cohomology and base change is to moduli problems, because it allows you to get consequences like this. And maybe that for us, the nice consequence is that you have a very ample line bundle, so you can embed. So if we define E to be the vector bundle, which is the push forward, then you have this embedding from C into the projective space over S. So it gives us an embedding into a projective bundle over S. And this is what will allow us to prove that MG is a stack over the big Ital topology, at least if the genus is at least 2. And I mean, let's only work on the second axiom because we've already seen that morphisms glue. So, so what we need to show is we have maybe a scheme S, and we have an Ital cover, Si. We have family of curves, Ci over Si, such that, and isomorphisms on their pullbacks. So I can take Ci, restrict it to Sij, and I have isomorphisms to Cj restricted to Sij. And let's just maybe call this one Cij for convenience. And let's set Ei to be the push forward under pi I of the relative canonical. Well, let's take the third power. And so this gives us a vector bundle Ei over Si. And let's note that we know that if I take Ei and I restrict it, pull it back to Sij, then by properties of the relative canonical is that this is equal or canonically isomorphic to the relative canonical of Cij over Sij, which is in turn canonically identified with the pullback of Ej restricted to Sij. So in other words, we have isomorphisms between canonical isomorphisms between Sij and between the pullbacks of Ei and Ej to Sij. And so Ital descent gives us a vector bundle E on S. And so here we're using like Ital descent for quasi-coherent sheaves. We have precisely the gluing data to glue these EIs to some quasi-coherent sheaf E, and then it's just properties of like being a vector bundle is also Ital local. So what you have is a vector bundle, and so you can take its projectivization PE, which lives over S. And note that important point here is that these CIs also live in these projectivizations of EI. And so and now we can get started because everything here is embedded into projective space. We now have that maybe a hope for gluing them together. And so what we'll use is effective descent for closed immersions, which I've highlighted here, which is the following statement that if I have an Ital cover XIX of a scheme X, closed subscheme Zi of Xi, such that on pullbacks they agree, and here we can say equality as closed subschemes, then they glue to a closed subscheme. And if you think about the data of a closed subscheme is like an ideal sheaf, or you can think about it as like the structure sheaf of that closed subscheme. And if you apply Ital descent to that quasi-coherent sheaf, you can then descend either the structure sheaf and therefore descend the closed subscheme. But the upshot for us is that we apply this in this setting where these closed subschemes are the CIs, and effective descent gives us a C over S. And so we've constructed C over S. And then finally, a tau descent will imply that this has all the properties we want, that it's a smooth family. Like the conditions of smoothness, properness are a tau local, and you can also, and also the condition, this is a condition on fibers too. So that's also, that's also local. All right, but yeah, so that sort of concludes the proof. And so now, now we've introduced stacks, and we know that MG is a stack over the big tau topology.
So does this more generally show that you have descent for pairs of schemes with an ample line bundle?
Yeah, exactly, yeah. Or maybe if you wanted to look at canonically polarized, if you restrict to varieties whose canonical line bundle is ample, and you know some sort of boundedness statement that there's a fixed power that gives you an embedding. Yeah, then you also get that it's a stack. Good question. Are there other questions on this? All right, there's one more example I want to give, which is quotient stacks. Oops. Oh, here we go. And I said something last time about this. So here we're in the setup where we fix a group scheme G over S, and I'm going to impose, for a reason that'll become clear later, that smooth and affine. And let's suppose that G acts on a scheme X over S. And last time what we defined, and then you can, I guess, you can functorially think about this as an action of G of T on X of T for all T over S. And last time we defined this pre-stack formally, but the important point was that the fibered category over a scheme S was precisely the groupoid quotient of this action. Oh no, I shouldn't say S, I should say T, is X of T over G of T. And maybe as an exercise, show it is not a stack. Say on the big tau topology of S. And maybe one way to think about this, okay, maybe let me give you a way to think about this, is that, well, what is an object? Let's suppose we have in a tau cover, and an object I say over Ti, well, is really just a map from Ti to X. That's what an element of this category is. But we can also think about this. Let me think about this in a different way, I can also think about this as taking the trivial G bundle, like if I take G cross Ti over Ti, and then I have a map induced into X, which I just take the map from Ti to X, but then since G acts on X, I can move it around. I get a map from G cross Ti. So this map is G equivariant. And now you might be able to see what goes wrong in this being a stack, because if I have a bunch of these, bunch of this data, it's a bunch of these trivial G bundles. Like they're not going to glue to the trivial G bundle; they'll glue to some other G bundle. So the point is that this, in the end, will glue to P over T to a G bundle. This is sort of motivation. But let me precisely define G bundle, and let me precisely then define the quotient stack. So this is an important notion that we'll use in the class. It's something that maybe you don't see in a first year course on schemes, but it's something that's like, it's a very conceptual notion that appears all over mathematics. And that's like the notion of a G bundle. And what it is it's just, it's a scheme P together with a G action. So G acts on P, and such that this map is G invariant. And the definition is going to be that essentially that the action of G on P is free and T is the quotient. But let's formulate it geometrically, just saying that there's an étale cover Ti to T such that it becomes trivial from G cross Ti, and such that this is a G equivariant isomorphism. So yeah, that's our notion of a principal G bundle. And I spell out in the appendix like a couple basic properties of this, and I relate this also to the notion of a G torser, which is a slightly more general notion that's equivalent in some cases. Great, but let me just go for it. Let me introduce then this quotient set. So we define X mod G over category of schemes over S, and objects is going to be the data of a principal G bundle together with an equivariant map to X. And then morphisms from, say, P to T to X to P prime to T prime to X should be the data of Cartesian diagrams such that, so if this map is F prime, this map is F, such that this commutes. And the result here is this proposition. I'm not going to prove is that this is a stack over the big étale topology. And the reason this is exactly like is descent is that you have descent for principal G bundles, and maybe an important point here is that the descent statement is a lot easier when G is affine. And so I'm using that here. That, well, first of all, I'm using that G is smooth because I'm just dealing with the étale topology. For non-smooth group schemes, you want to work with the flat topology to introduce G bundles. But for the affine condition on G to S is imposed. It forces every principal G bundle here to be affine. So these morphisms here are affine. And so therefore you're gluing together like algebras, which reduces to reduces to the descent for quasi-coherent G's. And then you can also descend the action of G and so forth. So we're really using the full machinery of descent for G bundles to get it to be a stack, but I'm not spelling out all the details here.
Or just being just a pedantic question, nowhere did you say G was, maybe it was a previous page, but you didn't say G was affine.
Oh yeah, I did. Well, I did here, but it was hidden. Yeah.
And the second question or comment is, it seems that I realized from things in the comments that nowhere at this point are you using, you could just do everything up until right now in the course or in the Zariski topology. The other topologies currently are not, you never use them. I mean, you will use them, I know, but all these statements seem perfectly happy in the Zariski topology if people don't want to be scared.
Yeah. Oh, so you were saying if I relax the smoothness and the affineness condition, like if I had no condition, then yeah, you're right. I wouldn't know that then there's stacks in the big Zariski site.
But I mean, also, if everything you say without relaxing anything, if people are scared by the flat topology, so far everything you're saying is already interesting in this Zariski topology, the stacks, like everything.
Yeah, that's right. Yeah, this already are interesting statements in the Zariski topology. And I guess, yeah, I don't really want to talk much about the flat topologies. I'm just going to always, when I work with group schemes, I'm going to have a smoothness hypothesis, and there's technicalities and positive characteristic that I'm going to avoid. Although, yeah, and but with more work, you can get basically the same statements to hold. So yeah, a lot of what I'm saying is interesting in the big Zariski site, but it's also interesting, like as I was trying to point out, that some of the stacks are like, yeah, everything is a stack in the big Zariski site, but only some of them are stacks in the big Ital site. Yeah, and like to get the MG is a stack in the big Ital site, we had to work a little bit. We had to use some geometry of families of smooth curves to show that you can descend them. Right. Okay. I'm actually going well for time. I have a few other things to say, and then I can wrap up. The first is I wanted to then revisit fiber products in the context of stacks, but it's no different than with the case of pre-stacks. And so here there's this lemma I'd encourage you to do, which says that if you have stacks over a site S, then the fiber product is also a stack. And I'll give some now examples of stacks in the context of quotient stacks. So maybe here's some exercises. You know, if I was teaching this graduate course in person at UW, I'd be working out a lot more of these details on the blackboard. It's a different style than I usually have, where I'm just stating a lot of exercises and relying on you to work out the details. The first exercise is that if I take, suppose I take x to x mod g. First, you should think about what this morphism is and how you define that. Again, I'm viewing this x as it's a scheme, but I'm viewing it as a stack. And then the exercise is to show that the fiber product is g cross x. And you should also try to work out what is precisely the two isomorphism giving the two commutativity of this diagram. So this may be the first exercise. The second is another nice diagram. If I take the diagonal of x mod g, x cross x, then the fiber product is g cross x. And the third property is that if for any G bundle, principal G bundle, say P over T, then there exists, we know that T then maps to this quotient stack by the 2-unita lemma. And the statement is that you get a Cartesian diagram like this. And so what this sort of says is that this is the universal G bundle. And let me say that again, it's the universal G bundle. Like this is the sort of, I want to really highlight that. It's just a sort of spectacular consequence. And one of the reasons why we introduced this machinery to begin with, we now have this object that's a stack, x mod G, we don't yet have too much geometry on it, but we will later treat it as a geometric object. And we have this projection from x to x mod g, and this is a G bundle. And so And one nice thing about G bundles is is that you know, with G bundles the action is always free, and then you're taking the quotient of the free action. Here, this action on G on X need not be free, but nevertheless, the quotient X mod G is such that it's like the action is free on X over X mod G. Yeah. This is this is the universal G bundle. And maybe an important example to think about is the case where X is trivial, and so like a special case of X mod G is BG. Well, I think I'm. Okay, I should have said something in addition that maybe you guys missed, or maybe you saw it. So I said something wrong here. So for this third exercise, the starting is I have a G bundle and I didn't specify, and an equivariant map to X, right? This is the part of the data of X mod G. And then the exercise is to show that this is F. This is the Cartesian diagram. And so an important special case is when X is trivial, and then you see that in that case, like the map from S to the classifying stack is the universal G bundle. So sorry for making that more confusing than it had to be. And the last thing that I want to say is the analog of sheafification, which I'll cover quickly, and that's stackification. And so, yeah. So stackification is the statement that you could take any pre-stack and associate to it a stack that satisfies a universal property. And one way to say it is that there's this equivalence of categories here. But another way to think of it is that you have, you know, for any pre-stack X, there should be a map to the stackification XT, which satisfies the universal property that for any other map to a stack X, that there exists a map here. But now, since we're dealing with stacks, we have to say that there should be a 2 arrow. And maybe the easiest way to say this universal property is just to say that this is an equivalence of categories. And the proof is not hard. I'm only going to sketch it. I think Robbie might disagree with me, but I'm going to say it's a 2-step process. But but it's really, it's also 3.
Yeah, I'd say I disagree with you. It's a 3-step process.
Yeah, it depends how you count. So
I count starting from 0.
So the first step, 1, is to first construct a map X, say to X1, where this is a pre-stack where morphism's blue uniquely. Where, like, in other words, where axiom 1 holds. And such that it satisfies the corresponding universal property to all such stacks. And the way we construct it is we're going to take the objects of X1 to be the same as the objects of X. And then I'll say that for then maybe then a map from A to B in X1 over maybe a map of schemes S to T is by definition an element of, well, if you wanted to know what a map from A to B in X was, it's an isom between A and F pullback B. Well, let me pause for a second, and just say this, that, as always, if you're seeing this for the first time, it's nice to think about simpler cases. So if some of this, it's often easier to think about the fibered categories. So if this generality confuses you, just think about the case that S equals T, where F is the identity. So a morphism in X is yeah, by definition, an isomorphism like this in the fibered category over S. And then we declare a morphism in X1 to be, well, I take the corresponding functor, the isom functor, which is this is now a pre-sheaf over schemes over S, and then I sheafify it. We already have sheafification in this site, and then I evaluate it at S. And so this, almost by definition, I'm basically sheafifying all morphisms. So what I obtain is a pre-stack where morphisms glue. That is where the first axiom holds. And then the second part is then you construct X1 to the stackification. And so, yeah, this is here what Robbie would point out is really this, because this involves sheafification, this is really a two-step process here. And then in the final step, now we need objects to glue, and we just do this sort of formally. We formally define an object of the stackification as a bunch of data, sort of like what we did with sheafification. So an object is going to consist of a triple where, like, first you have an ital cover, and now you have maybe objects AI, these are objects over SI, and then you have isomorphisms and these are required to satisfy the cocycle condition. So in other words, you construct something where you force the objects to glue. And I'll end with this exercise that if you take the pre-stack X mod G and then you stackify it, you get something equivalent to what I defined as the quotient stack X mod G. So I'd like to end here, but now I'll take questions and we can have a discussion. I'll stop the recording.